however he does it. Mr. Charlie Miller, Principal Analyst of Independent Security Evaluators. Now, a quick intro before we begin. He's the Principal Analyst, as I've mentioned. He's for Independent Security Evaluators, best known as the first to publicly create a remote exploit against the iPhone, and has discovered flaws in numerous applications on various operating systems. He has spoken at the workshop on the economics of information security, Black Hat, DEF CON, TourCon, ShmooCon, and CanSec West. He has authored the book Fuzzing for Software Security Testing and Quality Assurance, and the forthcoming The Mac Hacker's Handbook. He won a MacBook Air by winning the Pwn2Own contest in 2008 for breaking into a fully patched Mac OS X computer, and has a PhD from the University of Notre Dame. Mr. Charlie Miller.
Thank you. Thanks for the introduction. Thanks for coming. I'm going to talk to you about iPhones and iPhone security, and I brought two iPhones to play with. So it's fun to go through the security checkpoints in the airports when I have two iPhones and I have two computers. So they always think I'm up to something, and I guess I am. All right, so that great introduction, I'm just going to skip most of the stuff except Mac Hacker's Handbook, me and Dino Daizovi. It's coming out, not probably in January, but sometime. It's going to be good. All right, so what am I going to talk about today? Basically, I'll start with some iPhone basic stuff, you know what it is, and then I'll look at the App Store and anything that's relevant there. Then I'll move on to talk about how you look for bugs in the iPhone, how you exploit them, and then different things you can do once you're running code on the iPhone. All right, so the very basic stuff. So what's the iPhone? Well, it's the phone that Apple produced. So it's slick and cool, and all the cool kids have it. It runs basically a stripped-down version of the same thing you would get on the desktop, except the processor is different. So it's an ARM processor. It has 128 megabytes of RAM, and depending on what model you get, it's got flash memory for storage. And at least in the US, I think everywhere, it's locked to a particular carrier. Okay, so what's bad about the iPhone from our perspective? Well, the first thing is it's locked out of the box, and the 3G ones are still pretty much locked. As far as a little computer, which is what it is, it lacks a lot of the basic stuff you would want. So it doesn't have a shell. It doesn't have LS. So basically, if you break into it, if you could get a shell on it, there's not much you could do. So if you can't type LS, you're kind of in trouble. Also, applications and libraries on it will only run if they've been signed by Apple. So those are the bummers. All right, what about this carrier locking I'm talking about? So basically, if you get an iPhone in the US at least, you have to use AT&T or else it won't work. Of course, there's ways around that. The 3G one right now, they still don't know a way to unlock that with software, but there's some hardware things you can do that'll unlock it. The 2G ones, the basic software that you use to jailbreak it, which I'll talk about later, will unlock it for me. And my one here is unlocked, but it's not that great. Okay, so what is this jailbreaking business? Well, jailbreaking is a process that allows you to access to the file system, and so you can put files on it and do other stuff. There's a program called QuickPwn that works against the latest firmware for the iPhone. Some of the things it does is it changes the partitions around a little bit for you. It installs programs that allow you to install other things. So some of the other things that are available for it that you can install. So these are programs that people have built already for you. You can put SSHD on it, so that's nice. GCC, GDB, Python. So lots of things you might want to use. And it also turns off a lot of the code signing. So if you've jailbroken your iPhone, then you can put apps that you write on it, and they'll work. So that's nice. Okay, so what's the inside of this thing look like when you start digging around? Well, once you have a shell like I have on this screen here, now you can start looking at some of the processes. And I said it's a stripped-down version of Mac OS X, and it's true. If you're on PS, you see a lot of the same processes. It's like LaunchD, MDNS responders there. But there are some things that are specific to the iPhone you'll see. So here you'll see Springboard. So Springboard is the GUI for the iPhone. It's like, it's the window manager. And then you see mobile Safari as opposed to Safari, and mobile music player as opposed to iTunes. So it basically a lot of the same stuff, just stripped down versions of it. And then you'll see this launch from SB option, SB being Springboard, of course. Okay, what about the file system? Well, if you do an LS, it basically looks like your desktop. So, again, not too surprising. What are some of the more interesting iPhone-specific files you might care about? So this is a list of some of them. So they're all SQLite 3 databases. Call history shows all the calls you've made. Notes is like the little sticky note type application, all the information there. You got your voicemail, address book, pictures in your address book, and then your calendar. So this is basically all the files you would want to grab off someone's iPhone if you broke into it. Okay, so like I said, that it's this, these things aren't just flat files, they're these SQLite 3 files. And here's an example of me running SQLite 3 and dumping out the contents of the SMS database. So you see it's got some stuff about the structure of the actual databases that it contains, and then it's got some of the actual lines. So if you look at the bottom two, what's bolded is it's the phone number that the text message came in from, and then the data. So yes, it's snowing here. It probably doesn't snow here much, but it snows where I live. And then it talks about my kids and stuff. So yeah, this is you could just dump this file and get everyone's text messages. And the interesting thing is, I don't know if this is true anymore, but at first, at least on the iPhone, even if you cleared all of your text messages, they were still in the database. So even if a person was very careful to delete all their text messages, if you got on their phone and got this database, you would still see all their text messages. This is something that you'll see on the desktop version of macOS X2, but it's on the iPhone as well. So there's some programs that have to do with DRM that they don't like you to debug, and FairPlay-D is the one that's in charge of DRM on the iPhone. If you try to attach to it, it basically just makes GDB crash. So that's no fun. And the way that this works is because macOS X has this PT deny attach option that you can pass to ptrace. And what that says, I excerpted the MAM page here. What it says basically is if anyone's already attached to you and you issue this ptrace command, then bail. And if no one's attached to you yet, if they try to attach, then you segfault them. So that's not nice. But of course, there's ways to get around it. The normal trick you do on the desktop is you just run it inside of a debugger, and anytime they call ptrace, you make sure that you don't actually do what they want. You can't do that here because FairPlay-D is launched. The way it's launched, you can't run it in a debugger in time to catch the ptrace. So the way you have to break it is you basically need to modify the lib system where ptrace lives such that it doesn't actually go in far enough down to call the kernel to activate it. And then you need to modify FairPlay-D to where it calls, or it loads the modified libc as opposed to what they call lib system on Macs. So they install the modified one as opposed to the real one. So, and that's how you can beat that if you want. I don't know why you would really care, but just so you know. Okay, so what about building apps for the iPhone? Well, there's a few ways you can do it. So one is there's actually something you can download that someone built GCC for you, so I can show you that if you want. So they actually have GCC on your iPhone if you want, so you can build stuff, but it's super slow. You can do it from your desktop. You can build the whole tool chain, like you get GCC, Make, GDB, whatever you want. And there's a project on Google Code, iPhone Dev. Or if you pay to become an iPhone SDK member, then you get Apple's version of GCC, and it'll cross-compile and build stuff for the iPhone. That's the best way to do it, but you have to pay, and you have to sign their NDA and all that stuff. So whatever you want. Okay, so what about code signing? So on the iPhone, only signed applications will run, signed by Apple's private key, which you don't have, obviously. But as a developer, you can, they still want to allow for you to, test your applications on the iPhone. So they have to allow some way to do this, right? This is what happens if you try to run something that's not signed. So I try to run my program, and it just says killed. So you can't do it. So what you do is if you want to develop for them, you of course sign away your life in the NDA, and then you get a certificate from them. And what you can do is you can tell it like, okay, this is my iPhone, so I want my certificate to work on this iPhone. So at that point, once you do that, then your iPhone you can think signed by Apple or you work on the iPhone. Again, I say here, so at that point, your certificate will work on your phone, but nobody else's. But Apple's key works everywhere. And the applications that you download from the App Store are signed by Apple's key, so that's why they work. So there's this one other way that you can do it. So like what if you're a developer and you want to sort of distribute it to a bunch of people so they can test it for you? And the way that Apple set this up is called ad hoc distribution. So basically, like you can have a beta tester give you their this particular, it's like a serial number unique to the device called the Unique Device Identifier, UDID. So if they give you that, you can create a certificate and you give them a particular file to put on their phone. And at that point, their phone, it's like they've been provisioned for you, but you didn't have to actually plug them into your computer. So there's a limit of 100 people that can do that for you. But what you can do, and someone actually had a website that did this for a while, but it's gone now, so I imagine that Apple got mad at them. So what you can do, though, the limit of 100 is sort of weird. So say you have 100 beta testers and you have one more person who wants to join up. You can just remove one of your old beta testers and add a new one and ship it out to that guy, and it's going to work. So then you can you can have more than 100. It's just you have to do something every time. That's sort of a pain. So like I said, there was this guy, and I give the link here, and what he did was you could send him your UDID, and he would send you, the file you need to install his program. So he had like thousands of beta testers, right? Really, it was just a way for him to distribute his application without using the App Store. But I think he got in trouble. But the reason I bring this up is, what happens if you want to run something and you don't, you're not Apple, right? And say you're a bad guy and you're breaking into someone's iPhone. Well, obviously your shellcode doesn't have to be signed because it's running inside assigned processes, process space. So like whether it's Safari or whatever. So that doesn't need to be signed. But what that code can do is it can get the UDID of the compromised device. So there's APIs that allow your code to do that. So the shellcode can get the UDID. It can send it home, and then it can, back at bad guy headquarters, you have the guy's UDID, and you just pretend he's going to be your beta tester. So you take whatever binary you want to run on his phone, you sign it with your certificate that's been provisioned. With your certificate that's set up for that ad hoc distribution. You put that binary on his phone along with that mobile provision file, and then all of a sudden you've got something that runs on his phone. So why would you want to do that? Well, shellcode can do whatever it wants, so in some sense you don't need to do that, but writing all of your payloads in assembly is sort of a pain, so it's easier to write it in a higher level language. Also, your shellcode, it's only running while the phone's on. So what happens when he reboots or whatever? So if you can drop binaries and libraries and stuff on his phone, that's better because then when he reboots, you're always there. You get persistent access to the phone. So that's why you might want to do that. Okay. What about if the phone's already jailbroken? So I said that when you jailbreak it, it removes most of the code signing, but not all of it. They leave a little bit in, I guess just because they were lazy. They could have removed it. So this is an example. So there's a program called LDID. That if you run that, it fixes up the binary. It doesn't actually sign it, but it fixes it up enough that it'll run. So here, I try to run test, the same one that's not signed before, and it doesn't work. Then I run LDID, I run test, and then it works. So that's how it works on jailbroken phones. That's easy. So if you're breaking into guys whose phones are already jailbroken, you don't really need to worry about signing. You can just run LDID on the thing and then drop it on their phone. Okay, so that's basically all the basic stuff. So what the iPhone is and what it does. Now I'm going to move on to sort of more security-related stuff. So the first thing is, if you want to break into people's phones, you need to find bugs in their phone. And how do you find bugs in the iPhone? Well, like I said, it basically runs a stripped-down version of Mac OS X. So that's sort of the first place you can look. Much of that code's the same, except it's actually a much smaller attack surface, so it's harder to find bugs on the iPhone than it is on a Mac, for example. So what listens on the server side of the iPhone? Well, I already mentioned MDNS responders there, and it's just like the desktop, so it's sitting on 5353. And you know, as you might know, MDNS responder is used to set up, to configure devices without having to do anything so automatically. So it's just listening, and you know, if it gets one of these packets, it knows I see a printer or whatever. It also has something the desktop doesn't have. It has universal plug-and-play listening. And it's listening all the time, but this port's used when you're doing syncing. Then it's got some other process. I don't know what it is, but it binds to some different port every time, so it must be like, you know, initiating a connection. I don't know, but that's always there, and I don't know what it is, mostly because this is one of the drawbacks of doing this embedded work, is you don't have all of the tools you would normally have. Like on my desktop, I would run LSOF, for example, but they don't have that for iPhone, and I'm too lazy to build it. So I don't know what that is, but there's some other process you could nail remotely. Obviously, you still got the other stuff like the TCP/IP stack, the wireless stack, Bluetooth stacks. So you know, there's other code you could hit remotely, but there's not much, right? So there isn't much on the desktop Mac, and there's just as little, actually a little more, I guess, on the iPhone. But still, it's gonna be tough to just remotely nail iPhones. If you run Nmap against it, Nmap knows what it is, and it can detect it. All right, what about the client side? Well, just like on the desktop, there's a lot more available on the client side. So you've basically got mobile versions of a lot of the same programs you would have on the desktop. So there's mobile Safari, mobile Mail, mobile music player, mobile SMS, which is their text messaging application, mobile Slideshow, which is their basically iPhoto for the iPhone. And if you want to find anything else, just look in applications/mobile. And of course, the other thing you have on the client side is anything that they were stupid enough to download from the App Store, right? So, you could imagine, finding writing some game, getting it published on the App Store, and knowing that there was a bug in it that you put there or something. And whenever anyone downloads it, then you can, not only do you get their IP address maybe because they have to call out to you for something, but then you just nail them. Right, so I mentioned that it's a smaller attack surface. So what exactly do I mean? Well. So there's a lot of files. So basically, the biggest difference is there's no QuickTime on an iPhone. So like all the hundreds of file formats that your Mac can handle because it has QuickTime, iPhone can't. It also doesn't have Java or Flash. So those are the three big things. So if you can find a bug on a Mac that isn't QuickTime, Flash, or Java, then it's probably going to work on iPhone. But otherwise, you're out of luck. So like I say here, so there's some files that work on Safari, but not on mobile Safari. So SVG is one that's one's not in QuickTime, but it's just not compiled into mobile Safari. JP2 is a QuickTime file format, and so on. But interestingly, there's some file formats that will work on mobile Safari, but not the real Safari. And examples of that are the Microsoft format. So on mobile Safari, you can actually surf to a page that has a .doc, and it'll render it for you. But in real Safari, it won't. It'll try to download it. Besides Safari, you got other applications that are phone specific that you get on the iPhone. So you get it has to be able to handle SMS messages, for example. So if you could find a bug there, that would be a way in. And like I said, so Apple always says that, oh yes, iPhone is so different. Just because you find a bug, it's not going to be on the iPhone. Well, they're wrong. It's true that if you find a bug on, like I described, that isn't QuickTime and it isn't Flash or Java, it's going to be on the iPhone. And there's actually, after the Pwn contest, so this was, I found a bug in the JavaScript engine, and I got into Safari with it, and they asked me, they said, so is this bug, and I reported it to Apple, like a good guy. And I said, is this bug on iPhone too? And I said, I don't know, but I imagine it is. And I was out of the country, and I didn't want to use my phone because I didn't have the international plan. So they just left it at that, and it turns out that they were convinced it wasn't in it, even though, like I described it, it is. So like months later, I called them, or I told someone, I was like, I can't believe they haven't fixed this bug yet, right, some reporter. I was like, they've known about this bug for 2 months, they haven't fixed it. And like I said, it turns out they didn't believe that it was there, and it was. So don't trust Apple. Trust security researchers. Okay, so my favorite way to find bugs is fuzzing. So what about fuzzing for iPhone? Well, if you can find what Safari and mobile Safari have in common, you can just fuzz the desktop version of Safari and find all the bugs that way. And that those bugs will translate over to iPhone. So of the like 2 exploits I guess I've written for iPhone, so I didn't find either of those like on the iPhone. I found those on the desktop, and then I just wrote them for the iPhone. So like I say, so crashes in Safari should crash mobile Safari. What about on the phone? So what if you want to find a bug in SMS, or you want to find a bug in Microsoft Word, or not, in the mobile Safari handling of Microsoft Word? Well, there you're going to have to do it on the phone. So there you can actually fuzz on the phone. It's just like slower and sort of a pain. Also, I'll go into it, but it's harder to launch things from the command line there because of the whole springboard. And also, one other option is you can fuzz on the emulator. So if you signed up for the SDK, you'll get an emulator, and you can actually fuzz on there, and it's a lot easier. And that's actually how I found, so you may know I found this Android G1 phone bug last week. And I found that on the emulator, and I actually wrote the exploit on the emulator. And then when I got the phone, the exploit just worked without change. So emulators are cool for that. Okay, so how do you launch an application, a GUI application on the iPhone from the command line? It's actually not as trivial as you would think. So the window manager springboard, it sits there and listens on UDP port 30,000. And it's pretty cool. So the way that it works is you send it 256 bytes that contains the application identifier for the application that you care about. And you can get that from the info.plist file. And then Springboard will just launch that application. So the question is, so there's this port that you just send it what you want to run, and it runs it. And can you use that? It only listens on the local interface, though. So the question is, can you somehow use that to your advantage? I don't know. If Flash was on there, you could through the browser talk to that port, but I don't know if there's any way you can take advantage of that. But it's interesting. So here's some C code that will launch, in this case, mobile Safari from the command line. So all it does is send a packet like I described to that port. And the application identifier in this case is com.apple.mobile Safari. So you compile this, run it from the command line, and it'll launch Safari. Okay, so if you've ever seen any of my fuzzing talks, I always talk about how I love Crash Reporter, because it basically automatically finds when any of your programs crashes and gives you the crash dump for it. Well, there's Crash Reporter on iPhone too. It doesn't have the cool GUI that pops up and makes you feel all proud when you find a bug, but otherwise it's basically the same. So there's these 2 directories that I list here where the crash dumps will show up. One for if your program is running as the mobile user, which most things that you care about are, and then ones that are owned by root. These crash reports are plist files, which are the fancy Mac way to store data. And there's links in these directories that always point to the latest crash, and you can see what those look like. Okay, so then how do you fuzz? Well, one way you can do it, and I'll show you this, although it's going to be kind of hard to show you on my iPhone, but I'll try. So you can make an HTTP server that just serves a page and forces the browser to meta refresh every second to a different image or a different doc file or whatever you want. And then eventually, so that works great until the browser crashes, which is going to happen pretty soon. And then what you want to do is have the web server smart enough that if it hasn't had anyone connect to it in a while, it goes off, SSHs into the phone and launches Safari again. So I'll show you that real quick here. I got to find the right phone. Like you're not really going to be able to see anything hardly, but I swear it'll be worth the minute it takes me to do it. So I have such a server. and I have a lot of code and stuff in this talk. So if there's if you want any of this stuff, just give me an email and I'll send it to you. Oops. Oh yeah. Sorry about this. Okay. Okay, so you probably can't see this, but if you look super close, so if you see the little blue bar going choo choo choo, that's it fuzzing. So like every second it's getting a different image, and eventually it's going to go away. And you can see like this nasty crack I have on my phone maybe. But anyway, so that's fuzzing on the iPhone. It's not the greatest demo. There's better ones, trust me. I'll show you like a cool demo by the end. That one's pretty lame. Okay, so that's how you find bugs, right? Is you fuzz either your desktop or the iPhone, and eventually you find a crash and stuff. So what about writing the exploit? Well, the very first iPhone exploit that I wrote was like 2 weeks after the phone came out. And back then, like people like to tell stories about how hard they had it when they were kids. Well, that's how it is for me. Like back then, it was like really hard. So back then, the only thing that I had was I had Crash Reporter, but the only way you could get files off it was if you would like power off the phone and plug it into your computer. So it wasn't like real easy. Again, you could access the file system, but not when the phone was on. I had a cross compiler for ARM, but it wasn't like super great. It wouldn't work all the time for the iPhone. And IDA Pro was really bad, so it was really hard to write exploits back then. So you basically had no way to actively debug what was going on in the phone. You could just send in data and then see what the crash report was. And every time you did that, it took like 5 minutes. But it was possible, and we exploited it, so that was cool. Now, though, life is a lot easier. So you have SSH, you have GDB, so you can just run GDB right on the phone. You have GCC. IDA Pro works like really well with it now. So basically, you have, no one should ever complain about writing iPhone exploits now. It's easy compared to how it used to be. But what are some problems that you run into? So say you have a Safari exploit and you want to port it over to iPhone. What kind of things can you run into? Well, one thing is there's going to be a lot more resource limitations on iPhone, and this is what happened with, I told you this story earlier about how Apple claimed that bug I sent them wasn't vulnerable on the iPhone. And it was because of this resource limitation. So I wrote the exploit for Safari, and so I malloc like a ton of buffers and do all this other stuff. And so when they ran the exploit, it exhausted the iPhone's memory and just aborted. So it never even got to the line that had the bad code in it, right? All it was doing was mallocing buffers and stuff. And so like, oh, it didn't crash, it's not vulnerable. Well, they weren't so smart. So what really happened was I just needed to change the exploit not to malloc so much stuff, and then it worked. So you have to be careful of resource limitations on the iPhone. You have bandwidth considerations, so maybe your exploit works great, on the wireless network you're on, but as soon as you're doing it over the cellular network, maybe it's too slow and you have some timing issue, so you have to worry about that. The biggest issue is your payload is going to have to be a lot different. So I already mentioned that, there's no bin.sh, so what's shellcode at that point, right? There's no shell. So you have to do something creative, and I'm going to spend a lot of time talking about that. This is something I just learned pretty recently. So on the latest versions of iPhone, the heap is not executable. So actually, the iPhone is like way more secure than the desktop computer at this point, which is, blew me away. So it's actually much harder now to write iPhone exploits than to write regular Mac OS X exploits. But this is like documented nowhere. It's just like a secret change they made and didn't tell anybody, but it's true. Okay, so now let me talk a little bit about this like feng shui stuff I like to talk about. It's a really cool way to exploit heap overflows, and especially in WebKit, which is the browser that's on iPhone. And then I'll talk about an actual exploit, and I'll demo one. Okay, so heap feng shui was originally thought up by Soderov. He did it for Windows. And the idea behind it is, and then I just ported his idea over to Mac. The idea is that the heap is like totally unpredictable. So depending on where the browser's been, the heap could be in like all sorts of crazy configurations. So how many pages did the guy go to? How many windows or tabs do they have open? You know, what sort of crazy JavaScript is running? So it's impossible to know what the heap looks like when the victim shows up on your malicious web server. But what you can do is you can make them run JavaScript, and with that you can sort out the heap for them. So the heap basically, I described it's really complicated, and it's all fragmented to pieces, but it's totally deterministic, right? It's not magic. The basic idea, it's complicated of course, but the basic idea is that each new allocation will show up in the first spot that it can fit. So the way that you take over with a JavaScript bug on iPhone or any WebKit-based browser is basically these 5 steps. So first, you defragment the heap by filling in all the holes. Then you create a bunch of allocations, free up every other one, and then put in application data in the buffers you control. And then you overflow your buffer. So if you do those 5 steps, you end up overflowing application data that you control, and then you can access and get control of the whole process. So I'll explain that in a little more detail here, and then I'll show it in real life. Okay, so how do you make these allocations? Well, there's lots of ways. Any way that you can force the browser to call malloc, basically. So maybe in an image, HTML. We're going to talk about JavaScript. That'll fill in any holes. You just keep allocating the same size that you plan on allocating eventually. You don't know where they are in memory, but eventually you know they're going to be next to each other. And then you free every other one. And then you know the next time that, again, you don't know where this is on the heap. You just know that there's these holes on the heap. And then the next time that allocation of that size is made, it's going to fall into one of your holes. So Dino knows that there's not a whole lot of protections on overflowing heap metadata on a Mac, but there are some. It's basically easier to overwrite application data if you can than heap metadata. So by making those holes, we make sure that we control the buffer that's being overflown. So if we put data there and then access it, we'll be accessing corrupted data. So this is some bytes. These bytes are actually from Safari, as opposed to mobile Safari. And this is what it looks like in memory when in JavaScript you call new number of something. So in JavaScript, number, it looks like that. I don't have a pointer, I don't think. But so basically what you get is 1, which is the number of things in your array, right? Then you get the next thing is something about sparse arrays, which this isn't, so it's 0. And then you get a pointer to your number object. So here's a buffer that if I overflow this pointer to a number object. And I guess I'll say a little bit more. So I overflow this pointer to a number object. This number object has a function pointer within it. So all I have to do is reference this number pointer. When I override it, instead of pointing to a number object, it points to some buffer I control. And then when it tries to call that function pointer, instead of calling the function pointer, it's calling a pointer I control, and I get control of the process. So that's how this heap punctuation stuff works in JavaScript. Okay, so I mentioned that I had this exploit, and this is the one I was talking about, that it worked on the desktop, and then I wanted to port it to the iPhone. What changes did I have to make? Well, obviously I had to change the shellcode and the no-op sled and stuff because it's a different processor. If you don't know that, you're in trouble. What else did I have to do? Well, I had this huge sled, like a huge no-op sled into my shellcode, and it used to be 1, 2, 3, 4, really big, right? And then I reduced it by 1 less 0 because it was too big before. If you tried to make a sled as big as I was doing on the desktop version, the iPhone would just quit and would bail. That's fine. The result is, though, that the area that you can land in is smaller, and so your exploit becomes less reliable. But it still works. Likewise, I talked about how in the feng shui you have to allocate a ton of buffers, right, to fill up all the holes and then to make the ones on the end that are adjacent. Well, on the desktop version, I allocated 1,000 of those buffers. I couldn't do that on the iPhone version because, again, I ran out of resources. So instead, I only allocate 100 buffers. And again, what this means is if your heap is really defragmented, like you have more than 100 of these holes to begin with, then the exploit's not going to work. So you end up with a less reliable exploit on the iPhone than you would on the desktop. The other thing which I didn't actually mention was there's this problem in JavaScript. You can't necessarily force a free because of garbage collection. So what I did was I just called sleep, basically. And that made sure that the garbage collection happened. Again, I couldn't sleep for as long on the iPhone version as on the desktop version. What else is different on when you write iPhone exploits as opposed to desktop exploits? Well, the actual overflow is a little bit different. The overflow was based on a regular expression, and so that was a little different. Also, the way the memory looks is slightly different. So they had used an older version of JavaScript. So remember before I said on the desktop version it looked like 1, 0, and then a pointer. Well, if you look at that top little excerpt from GDB, actually it's not GDB, it's some other debugger. But anyway, now instead of that, it just looks like it's just a pointer. And so there's not that little bit of metadata beforehand. And then if you look on the second little set of numbers there, that's what the number object looks like. And so you can see there's a pointer and then some number and some zeros and stuff. Well, that first pointer is actually pointing to code. So that's the function pointer that I want to get called. So that's it. So there's not that many differences when you want to port the exploit. Just have to be careful for resources, basically. And then this is a slide that talks about so when you first start putting these buffers in the feng shui, right? They're filling up holes. They're all over the place. But eventually, I said I allocated 100 of these buffers. By the end, they start lining up right next to each other, which is what we want. And here it's an excerpt from a debugger, and you can see that they start lining up right next to each other. So the first buffer is allocated at 975 something, and then the next one's at 976, and then 977, excuse me. So this is just showing that the feng shui stuff that I originally did on the desktop works on the iPhone too. Okay, so the takeaway from all that stuff is if you can write an exploit for the desktop, you're probably in pretty good shape for the iPhone. What about payloads? So payloads is much different on the iPhone. There are a couple payloads that Metasploit you can get. Most of those, I think, depend on the iPhone already being jailbroken. For non-jailbroken case, so like your typical person with a phone, you can still do anything, right? So your code is still running. You can call any system calls you want, whatever. But you have to so you can't rely on anything being there. So you can't rely on there being a shell or being whatever other program you might want to call. You basically have to assume there's no programs there that you want. So you just have to bring along all your functionality with you. And the other thing is, originally the iPhone ran everything as root, which was really stupid. Now they do something like only slightly stupid. So now they have two users. One called mobile, which does everything like you would ever want to do, like web browser, mail, text message. So that all runs as user mobile, and then the sysadmin stuff, that runs as root. So now when you break in, you get user mobile instead of root, but you still have access to basically all the data on the phone. The only thing you can't do is you can't try to jailbreak the thing on the fly anymore, which is probably why they did this, not for security, because they didn't want people jailbreaking their phones so easily. All right, so there's going to be tons of code coming up here. So let me just introduce you to ARM real quick if you haven't ever seen it. So in ARM, they have there's 16 32-bit registers that are called R0, they're R15. The last three have special names. So R13 is the stack pointer. 14 is the link register, which is used to store return addresses sometimes. R15 is the program counter, and that's what you think it would be. ARM is a RISC architecture, so that means there's not as many different kinds of instructions as there is on x86, for example. And they're all 4 bytes long. And since they're 4 bytes long, and most of the addresses are 4 bytes, that means that generally to put a full D word into a register takes more than one instruction. Not that big a deal. There's also this thumb mode that ARM processors can do, but I'm not really going to talk about that. Okay, so how do function calls work on ARM? Well, instead of jump and call, you can get B, BL, BX, BLX. So it's branch, and then BL branches and sets the link register to the return address, so you can get back to where you started. The other thing is that on ARM, this is kind of cool. PC is just a general purpose register, so the program counter. So you can actually move stuff into the program counter. Or if you want to know, like shellcode usually needs to figure out where it is in memory, so you can just like read right out of that register. You don't have to do any crazy jumps and pops and stuff. As far as function calls, the first 4 arguments are passed in the lowest registers, and any more beyond that are passed on the stack. What about system calls? Well, there's this SWI128 instruction, and that's what you call when you want to do a system call. You put the call number in R12, and then just like function calls, any arguments to the system call go in the low registers or the stack. So those 3 instructions are the equivalent of calling exit 0. So exit is, the syscall is 1, exit of 0, so the first argument goes in R00, 0, and then you call SWI128. Okay, so what is some shellcode? So now I'm going to do like some payloads, and then I'll do some demos of, actually, yeah, I'll do a couple demos. So, well, one thing you might want to do, and this is what the very first shellcode I wrote did, you might just want to steal all those files I talked about off the person's phone. And I don't know if you can tell, but this image is like from one of those places where you have to pay to get the image. Otherwise, it has the water stamp on it, or watermark, I mean. So I thought it was funny that I'm talking about stealing files, and I use an image. So what's the shellcode going to do? It's going to run. It's going to call back to the bad guy's server, and then it's going to open some file like the SMS database, read from the file system and write to the socket, close up, and you're done. So you can do this whole shellcode just with system calls. So this shellcode works on a jailbroken phone or a non-jailbroken phone. And there it is. It's a lot of assembly there. But if you look at the stuff that's, and again, if you want a copy of any of this stuff, it's actually all there. So when you get the slides are going to be available on the website. You can either just cut and paste it or just send me an email, I'll send it to you. So you can see all the system calls here, though. So it's socket, connect, open, read, close, write, close, exit. It's pretty simple. It's pretty straightforward. Okay, so what's something interesting about ARM? If you take that shellcode I just talked about and you write out the bytes for the machine code for it, you see this funny thing that in every 4th byte is E something, right? And that's not a coincidence. So it's a good trick for if you're just you're just like looking through memory with GDB or something, you can find what's machine code and what isn't just by this trick. And the reason that you get this is on x86, for example, there's these conditional instructions like you could jump not equal, right? So this has to do with whether condition code's true. Well, in ARM, every instruction has this ability to either execute or not. It turns out that the E means always execute. So those are instructions that aren't conditional, and that's usually what it is. So there's not that many times that you're just your typical instruction. They have to be super optimized to really take advantage of that. So usually you see all these E's every 4 bytes. Okay, so what about some shellcode that's a little more specific to the iPhone? Well, what if you want to do something with the phone, like itself, right? I could have stolen files from a desktop, but I can't like dial the phone, for example, if it's a desktop. Well, what about this? So you can just call right into the iPhone libraries that are on the device. So you could get the GPS and text messages, whatever you wanted. The way that I do this one is I call a function called audio services play system sound. The shellcode I'm going to show you is pretty lame, and it has that address hard-coded in. In a few slides, I'll talk about how you can not do that. Okay, so how do you know what the arguments to this function is? Well, thanks to IdaPro, I disassembled mobilephone.app, and I figured out what happened when a text message came in. And you can see what happens is it sets this value 3EA in the register R0, so that's the first argument to the function. And then it just calls the function. That's it. It's very easy. And if you look around for other instances that calls, it just puts in different arguments for different things, but 3EA just means beep and vibrate. That's what happens when you get a text message. Okay, and here's the shellcode. It's real straightforward. All you do is load the address, and you load 3EA into R0, the address into R7, branch to R7. So branch is like call in x86. And then you loop and do it over and over and over again. Okay, I'll show you my demo. So this is a phone. It's running an old version. So this is running version 1.1.4. So this is the one that the regex bug still works on. So I'm going to exploit that bug in Safari, mobile Safari, and the shellcode is going to be this vibrating shellcode, and you'll see it. So you'll hear it, really. That's why I chose this one. So I'm getting ready to go to the malicious web page. And this uses the feng shui, like I explained to. Okay, let's see if it's going to work here. There's my microphone. It's loading. I wonder if my address, oh wait, wrong IP address, I think. This demo works much better at my house, where the IP address doesn't change. Okay, let's try this. Come on. Let me make sure that I know my own IP address. Oops, like I noticed, if you can read the screen, I actually found a bug. But being the responsible guy, I won't tell you what it is. 10.0.2.1. I thought I tried that. Oh, 10.0.2.1. Well, give me like one more minute to think about this, and then we'll just have to move on. It's a really cool demo, though. I'll be like at the party showing you guys. Let me see if the web browser works here. 10.0.2.1. Let me try it one more time. 10. Is anyone on go to my wireless Charlie Miller's computer? I can exploit you if you have a phone. An old phone that you never updated. Well, we'll try to come back to this, and it only takes a second to run. I'll try to figure it out in a little bit. It's really cool, though. The phone goes berserk. Well, now it won't be as cool that it lived up to it, but hopefully I'll figure it out before the end of the talk. Okay. So what else can you do? So that was an example of calling iPhone-specific functions. Let's see, what else can you do? So you can also just mess with those database files I talked about. So I already showed you that they form in this SQLite 3 format. So you can just change those database files, and then what the iPhone thinks is reality changes. So you can add SMS communications that never happened. You can delete those. You can add people to the contacts. You can change contact information. So maybe you change the person's grandma's phone number to your phone number. So next time you call them, they think it's their grandma. Okay, so I wrote the shellcode that adds a note to their iPhone. So how does it work? Well, first you need to figure out the layout of this database, SQLite 3. Notes.db. So I run the dump here, and you can see what the database looks like. So it's got one table called note that has a creation date, a title, and a summary, and another table called note bodies that has an ID and data. Looking at that first table, note, it's pretty obvious. It's just some number and then some text. Right? That's pretty straightforward. The only thing is this number, like it's supposed to be a time, but it's not your typical Unix time you would expect. It turns out if you do the math, it comes from back in January 1st, 2001, which is what NSDate, which is a Mac thing, is based on. So basically you can convert it by doing this 973 or 978307200 number. Okay, what about the other database? Well, it's just numbers that start from 1 and increase each time, and then the data is HTML. So here is C code that will add a note to the iPhone's database. So all it does is call SQLite3 open on the database file, and then it execs those two SQLite commands. So first it figures out insert into note values the time minus that conversion number and then some data. And then the other one is it figures out what the last node ID was, adds one to it, and then adds data. Here it is in assembly. Okay, so there's one more payload I want to talk about. It's pretty cool, although you might have to come up later to see it since I'm having some not so much luck here with the demo. But anyway, so far I've been hard coding in addresses of functions, and that's pretty weak. So you don't have to do that. You can actually take advantage of the fact that the DYLD library is loaded at the same spot every time. And it contains code that can find every other symbol. So you can just take advantage of that. So this is a C program that will take in, if you give it the base address of DYLD, it will, and a symbol you're looking for, it'll give you the address where that's loaded, even if it changes every time. And this is basically decompiled something that Dino has in his talk probably. But basically, it just takes advantage of the mock file format and it figures out the symbol. So in this case, you can get rid of all that hard-coded addresses. And here is the assembly that does the same thing. I'm sure you can't read that, but again, this is supposed to be just for reference. If you want to take it. Okay, so the final payload is basically the equivalent of DLL injection for the iPhone. And so the idea is you write a bundle on Mac OS X, and then you inject it into the process space. Well, it turns out on the iPhone you can't really do it quite so slick. What I'm going to do is write it to disk and then call DL open on it. So it's not so cool because that ends up on disk, but who looks at their file system on their iPhone anyway? But in this, so you have the disadvantage that unless it's jailbroken, you're going to have to sign in on the fly, like I described earlier in the talk. All right, so basically all this thing does is it uses that Mako resolve function that I showed you before to find the address of DL open and DL sim. And then it just calls DL open and DL sim, and whatever code you want to run gets run. And I see. Okay. So why would you even do this? Well, it's cool because instead of writing in assembly, which as you saw can get complicated, right? You can write in C or Objective-C or whatever you want. And you can make some pretty cool bundles this way. So if it works, I'll show you how to turn your iPhone into a covert listening device. Other things you can do is you can register to receive GPS updates so that whenever the person's moving around, it'll call out to you with where they're at, so you can track your victim that way. You can make or record phone calls and do anything the phone can do. So okay, let me show you this demo if it works. It has a better chance of working. Maybe, I don't know. Let's see. So I'm going to SSH into the phone here. Oh, no wonder. Let me see. Okay, here, let me make this bigger for you. Can you maybe read it now almost? See, if I get this demo to work, I bet I can get the old one to work too because I didn't have the right IP address. I still don't know if I have the right IP address. Let me try to cancel out of this real quick. Okay, let's try this. Come on. Okay, well, live demos are not great. Anyway, so it's not working. That sucks. But let me try one last thing, and then I'll just let you go. I swear it works. You just have to trust me. I can show you what happens from the last time I did it, but pretty lame. Okay. Well, anyway, the network is like screwed up. So anyway, what happens is, so I have this bundle. Maybe I have it here. I'll show it to you. And what it does is it turns on the microphone for 2 seconds and records it, and then saves it to a file. The last time I ran it is, I'll show you what happens. So this is like, you could pretend that the demo worked, and then I got the file off the phone. This is what it's like. So yeah, so catch up to me later, and I'll show you the demo when there's not like people watching me, and I choke under pressure. Let's see. So you get this like file. It's a .caf. I don't know what that is, but it's just a sound file. And then
here I am in Malaysia.
So that was me testing it this morning. I swear it worked. Anyway, that's it. Sorry, like the demos all failed except the one you couldn't really see. So that's it. Questions? Besides, like, am I a total liar and stuff? But no, I swear it works. Catch up to me later. I'll show it to you. It's pretty cool. Okay. All right. Thanks.
Thank you very much, Charlie. And you will be around even at the reception.